Okay, so let's carry on with our lecture. In the previous part of today's lecture, we have been talking about the inverse Z transform. Now we will be moving on to discuss the properties of the Z transform. The first property here is the linearity property. It simply says that the Z transform is a linear operator. And this simply means that if we have a sequence x1 of n, whose Z transform is x1 of Z, and whose region of convergence is Rx1. And we know another sequence x2 of n, whose Z transform is x2 of Z, and whose region of convergence is Rx2. The property says that if we form a linear combination of x1 of n and x2 of n, that's to say constant times x1 plus constant times x2. This is a linear combination of the two sequences x1 and x2. Then the Z transform of this new sequence will be a linear combination of the corresponding Z transforms, that is a1 x1 of Z plus a2 x2 of Z. This is the linearity property. If we form a linear combination of discrete time sequences in time domain, the Z transform of the new sequence would be a linear combination of the corresponding Z transforms using the same constants A1 and A2. A1 and A2. What about the ROC of the new sequence, or the new Z transform? The ROC of the new Z transform contains the intersection of Rx1 and Rx2, Rx1 being the ROC for x1 and Rx2 being the ROC of x2. So ROC is simply the intersection of the two regions of convergences. The two that transforms x1 of z and x2 of z need to converge in a certain region. Both of them need to converge in a certain region, which is the intersection of the two ROCs. But the property here says it contains the intersection, or in the textbook it says at least the intersection. What is this supposed to mean? Sometimes when you combine two Z transforms like this one, something happens that's called pool zero cancellation. Sometimes a zero cancels a pool. In this case, when a zero cancels a pool, the ROC gets somehow extended. As we have learned before, the ROC starts and ends at pools. So if one pool is cancelled by a zero, then the ROC will extend to a larger area rather than just the intersection. So that's why it says it's at least the intersection or it contains the intersection. Of course, if the intersection is phi, which is the empty set, there is no intersection, we say that the Z transform of this linear combination does not exist. And we have seen a similar situation in a previous example when we had a two-sided sequence and we were trying to compute the Z transform. At some point we had a situation where the region of convergences do not intersect, or the intersection is phi. Then we said that the Z transform does not exist. Okay, the second property here is a time shift property, and this one is very important. Let's take a closer look at it. The property simply says that if we know a sequence x of n, and we know its transform x of z, and region of convergence Rx, if we shift the time domain signal x of n to be x of n minus k, then the Z transform of this sequence would be the same x of z, which is a transform of x of n, multiplied by a factor z to the minus k. And as you can see here, if it's x of n minus k, you multiply by a term z to the power minus k. Okay, so if it's x of n minus 3, you multiply z to the power minus 3. If it's x of n plus 2, so you multiply by z to the power 2, and so on. Okay, what about the region of convergence here? So the new region of convergence would be the same as the old region of convergence. So the new ROC is Rx, which is the region of convergence of x of z, except for z equals 0 if k is larger than 0, or except z equals infinity for k less than infinity. Why is that? If k is larger than 0, then you will be shifting this signal to the right. So if you remember, if we have samples of a signal to the right of n equals 0, we need to exclude z equals 0 from the region of convergence. That's why we will be removing z equals 0 from ROC if we're shifting right, because shifting right, we might be getting new samples located at the right of n equals 0. On the other hand, if k is less than 0, then we'll be shifting left. In this case, if we're shifting left, we might get new samples located left of n equals 0. In this case, we need to exclude z equals infinity. So it's basically the same ROC, but you exclude 0 if you're shifting right, you exclude infinity if you're shifting left. The proof of this property is straightforward, but let's ignore it for now and let's carry on. Okay, so now we have an example. Let's try to find the Z transform of the sequence x of n. X of n is defined as u of n minus u of n minus n capital. If you take a closer look at this sequence, it's so sort of a sampled rectangular pulse starting at n equals 0 and ending at n equals n capital minus 1. So we can solve this Z transform, we can find the Z transform in two different ways. The first way is using the definition, so summation from n equals minus infinity to positive infinity, x of n z to the minus n. In this case, since this sequence is 0 except for the range n equals 0 to n equals n capital minus 1, we do the summation from n equals 0 to n minus 1 of z to the minus n, and x of n of course equals 1. And if you do this summation, it's basically z to the power minus 1 all to the power n. It's one of the summations we know. It's basically 1 minus z minus 1 in the denominator and 1 minus z to the power minus n in the numerator. This is true if z minus 1 is not equal to 1. And if it's equal to 1, we will get capital N. And the region of convergence here is that z is not equal to 0, because this is a finite duration sequence and all the samples we have are located to the right of n equals 0. So we have to exclude z equals 0. We can also solve the same problem using the linearity property. So we can use the properties as follows. So u of n minus u of n minus 1. U of n, we can find the z transform of u of n by itself. It's basically 1 to the power n times u of n. And from the lookup table we have, it will be 1 over 1 minus z minus 1. And the region of convergence would be modulus z larger than 1. And for this sequence, it's a shifted unit step. So the same z transform here, and we will apply the time shift property. So we multiply by z to the power minus n capital, which is a shift. And then this would be having the region of convergence modulus z larger than 1, which is the same ROC, except for z equals 0, and z equals 0 is already not in this ROC. So if you combine these together, you will get 1 minus z to the power minus n over 1 minus z minus 1, which is the same expression we got here. And the ROC should contain modulus z larger than 1, contains modulus z larger than 1. And of course, if you can notice here, the ROC is kind of different. Here it says contains modulus z larger than 1, and here it says all z except z equals 0. The two ROCs do not contradict each other. Here it says it contains, or at least is range modulus z larger than 1. So it agrees with the previous ROC. And if we dig a little bit deeper, we will find that we have a 0 that will cancel this pool located at 1, and hence extending the ROC to cover the entire Z domain except Z equals 0. The third property we have here is a convolution of sequences. We have seen convolution in the signals and systems course, and we know that we know how to perform linear convolution in time domain. The property simply says that if we do a linear convolution of two sequences in the time domain, this is equivalent to multiplying the corresponding Z transforms in the Z domain. So instead of doing convolution in time domain, we can multiply the corresponding Z transforms in Z domain, and this might simplify the calculations a little bit. And the new region of convergence for the new sequence, which is a convolution, would contain the intersection of Rx1 and Rx2. This is Rx2, of course, not Rx1. And here again, the word contains or at least the intersection. It's happened, we say contains or at least because sometimes when you multiply two Z transforms like this one, you get a pool zero cancellation. And again, when a pool is cancelled, the ROC extends. So the proof is also straightforward, but let's ignore it for now and let's carry on with this example. So now we have a sequence x1 of n equals delta of n plus 2 delta of n minus 2. So we have the first sequence is one impulse at n equals 0 whose weight is 1, and another impulse at n equals 2 whose weight is 2. And x2 of n is delta of n plus 4 delta n minus 1 plus 2 delta n minus 2 plus 3 delta n minus 3. This plus sign should be removed. So the question is asking us to determine the linear convolution of x1 and x2. We can use the matrix form, of course. We have discussed this in the first chapter we have been doing in this course. So if we choose x1 to be the signal that remains as is, we will get 1 and then 0 and then 2. This 0 represents the sample value at n equals 1. It's 0. And then we use the sequence x2 to form the matrix here. So it's 1, 4, 2, 3, 1, 4, 2, 3, and then we append 2 zeros. And if you remember, the dimensions should be like this. This is 3 by 1, and this other sequences has 4 samples. So we expect the output to be 4 plus 3, which is 7 minus 1, which is 6. So this matrix should be 6 by 3. If you do the matrix multiplication, you will get this output, whose output is 1, 4, 4, 11, 4, 6. This one is happening at time 0, so it's delta of n. This is happening at time n equals 1, so it's 4 delta n minus 1, 4 delta n minus 2, 11 delta n minus 3, 4 delta n minus 4, 6 delta n minus 5. Okay, so now we've done the convolution as usual. What are the other options? The other option is to actually transform x1 of n to the z domain and get x1 of z and get x2 of z and multiply the two z transforms, because the property we have just been discussing says convolution in time domain is equivalent to multiplication in z domain. So if we get x1 of z and get x2 of z, and then we can multiply them together and do the inverse transform, we will get y of n. Okay, so doing Z transform from the lookup table, delta of n will have transform of 1, and delta n minus 2 would be z to the power minus 2. So it's 1 plus 2 z minus 2. Same for the second sequence if you multiply these together, because we want to find y of z, which is the z transform of y of n. So z transform of the linear convolution, which is multiplication, as the property says. If we multiply these two Z transforms together, we will get this expression. And if you do the inverse Z transform, this one would be transformed to delta of n. and this is 4 delta n minus 1. This would be 4 delta n minus 2. This is 11 delta n minus 3, 4 delta n minus 4, and z delta n minus 5, which is exactly the same sequence we got here from the linear convolution. This example is very simple. It's trying to verify the property which says performing linear convolution in time is equivalent to multiplying the corresponding z transforms in the z domain. So sometimes it would be easier to do the linear convolution in time. Sometimes it's easier to do the z transform multiplication in the z domain. Okay, the next property is the multiplication by an exponential sequence. If we know a discrete time sequence x of n and its transform x of z and ROC Rx, if we multiply the sequence x of n by an exponential sequence a, which is a constant, could be a complex constant, a to the power n, then the z transform would be x of z over a. So the z transform would be the same x of z, but we would replace every z by z over a. And the region of convergence would be scaled by modulus A, So if the region of convergence is, let's say, modulus Z larger than 1, you would replace Z by Z over A. So the new ROC would be modulus Z over A larger than 1, which is modulus Z larger than modulus A. So the ROC is scaled by a factor of modulus A. So in this property, when you multiply in the time domain by a to the power n, in z domain you replace every z by z over a. In the ROC, or the expression for x of z, you replace every z with z over a. And this will give you scaling for the ROC. And this will also result in expansion or shrinking and rotation of the ROC. So basically, when you multiply the sequence time domain by a to the power n, you result in expansion or shrinking of the ROC, and the location of poles and zeros, and you rotate the pole and zero pattern. And again, the proof is straightforward, but let's ignore it for now. And let's move on to the next property, which is differentiation of Z transform. If you differentiate the Z transform dx of Z by dz and multiply by minus Z, this is equivalent to multiplying the time domain sequence by n. Or in other words, if you have x of n and you multiply it by n, the transform of this would be to differentiate x of z and multiply by minus z. The ROC remains the same, doesn't change, and again the proof is straightforward, but we'll ignore it for now. Example. Let's say we have a sequence x of n a to the power n u of n, and we need to find the z transform of this sequence. Let's try to do it in two different ways. First way, let's apply the definition we have. The definition is that x of z is a summation from minus infinity to positive infinity of the discrete time sequence, which is n a to the power n u of n times z to the minus n. Since we have a u of n here, the summation would go from 0 to infinity. And combining a and z minus 1 in one term like this, we'd have n a z minus 1 to the power n, which is n r to the power n. And if you remember the summations we have discussed in the very first lecture in Z transform, this summation is simply a z minus 1 over 1 a z minus 1 all squared, where the ROC should be modulus z larger than modulus a. Okay, we also can solve this problem using the differentiation in Z domain property, because in the differentiation in Z domain property, you multiply a sequence you know by n. So here we have a sequence that we know, a to the power n u of n, and we know its transform. And we're multiplying this sequence that we know by n, That's why we can apply the differentiation property. So if we know a to the power n u of n, and we know its transform is 1 over 1 minus az minus 1, then if we multiply this sequence by n, we simply take this z transform and differentiate it with respect to z and multiply by minus z. So if we do the differentiation here and multiply by minus z, we will get the same expression we got from the previous method, which is a direct application of the transform definition. And the ROC would be modulus z larger than modulus a. So this example helps us to understand and verify the differentiation property. The next property is the conjugation of a complex sequence. If we know x of n, discrete time sequence, and we know its transform x of z, if we take the complex conjugate of the sequence, x conjugate of n, then the z transform would be x conjugate of z conjugate. What does this mean? It simply means that you, in the expression for x of z, you first replace every z with z conjugate, and then you apply a conjugate to the whole function. So first you replace every z by z conjugate, and then you apply a conjugate to the whole function. The ROC remains the same. The proof is straightforward, just 2 lines, but again, let's skip it for now. So no proofs in this section where we're talking about the properties of the transform. I will not be asking you for any proof. Okay, so the next property is called the time reversal property. In time reversal property, if we replace n by minus n, if we have x of minus n, this basically implies that in the z domain we replace every z by 1 over z. So if you know x of n and you know its transform x of z, if you have x of minus n, then you need to replace every z by 1 over z, even in the region of convergence. So if the region of convergence is modulus z larger than 1, then you would replace z by 1 over z. So it's 1 over z larger than 1, which is modulus z less than 1. That's why we say the ROC would be inverted. The ROC would be inverted. Again, the proof is easy, but we will skip it for now. Okay, and let's ignore the last property, which is the initial value theorem. Let's ignore it, and this basically concludes the section of the properties of the Z transform.